So I'm going to start, somebody asked, and then also for my online class in 3.2. I'm going to start recording the sessions that we have here, and I'll just post them on YouTube. And so on your website, you might actually already have it there, you'll have a screencast section. Let me see if I put it on there. No, but under video resources, you'll have, oh yeah, there it is. Under screencast, you'll have, no, that's not it. You'll have screencasts for the class, where it's just every day. That way if you miss a class, you can find out exactly what we covered during that time. The audio is not real great because I'm just using a little desktop microphone, but you can pick it out if you're just trying to pick up where we left off in class, okay? So I'll put that on the website this afternoon and start posting those to YouTube. If you want to use them, if not, that's fine too. All right, so we're going to move on now to chapter 5. Listen, I just want to give you a little heads up. We will have one more exam before the drop day. So if you're thinking about dropping, certainly don't do that until after the third exam, because after the third exam, you'll have a good understanding of where you are in the class. I always try to have most of our exams before the drop date. We will have 3 of our 4 exams before the drop date. So if you're thinking about that, honestly, I'm not sure that, nobody really needs to be thinking about that right now. You just need to try to do as well as you can on the next steps. Okay? Feeling okay today? Yeah, that was a tough test that we had. As a class, y'all did pretty well on it, but it was a tough test. It was, what, the second toughest test? The toughest test of the year? Was this harder or more difficult than the previous? About the same? Yeah. Harder, yeah. Okay, I think it's probably about the same, but a little more difficult. But that's okay. We're going to move on. Everybody be doing it if it was easy, right? All right, so I'm going to move on to chapter 5, which is on magnetism. And we're going to see some different stuff, really, from here on out. So after chapter 5 on magnetism, we're going to move into optics. And then we have a couple of chapters on optics, and then we'll do sound. So everything from here on out is a lot different from anything that we've seen really up to this point. We'll still see some electric fields in the magnetic field chapter, and still see a few things that are familiar, but a lot of it's going to be different. So that could be good news in the sense that if you didn't really get the previous chapters, then move past that stuff. But bad news in the sense that, well, this is just brand new stuff that we have to learn. Okay? But magnetic fields are pretty easy. We'll see some new sort of mathematical tools, and talk about a few other things. But first, just a little introduction stuff. Most of this you probably learned in, I don't know, first grade or whatever, but basic stuff about magnets. First of all, magnets have poles, and we call these north and south poles. Like poles repel. Opposite poles attract. I'm sure you used to play with your little Brio train sets that have the little magnetic connectors, right? You push 2 trains together and they don't connect, they repel from one another. While you put 2 other trains together and they click, right? You know what I'm talking about, the Brio train sets? You didn't have them, Zach? I'm sorry. Anyway, like poles repel and opposite poles attract. And monopoles do not exist. If you have a bar magnet like this, and it has a north and a south pole, for a long time people thought, well, you know what? If you split this up, then I'll get a north and a south pole, and then I get 2 magnets, and then if I keep splitting it up, I get a south and a north pole, I get 2 more magnets, and people thought, well, there must be a place where if I keep going, I will get a magnet that was so small, if I split it in half, I get a north pole over here and a south pole over here. That would be a monopole, where I just have one single pole in a magnet. But those don't exist, and it goes by the reason that magnetic fields exist is that they're created by moving charges. And so electrons, which are always moving, create their own magnetic field. They create a magnetic field. And so the reason that you can't have a monopole is because you can't split that electron in 2. So if I were to keep splitting that bar magnet further and further and further down, making it smaller and smaller and smaller, then eventually I'd just split it into 2 electrons. And I'd have one electron that would have a north and a south pole, and I'd have another electron that would have a north and a south pole. And since the electron is that fundamental particle, then I can't go further than that. My magnet will always have a north and a south pole. Magnetic domain, you might not have had this in first grade, but describes a region of uniform magnetization when a group of electrons are oriented such that their magnetic fields are all in the same direction. I'll show you a picture. You know what? I have an electron here. This electron has a magnetic field vector that points in this direction, north up here, south up here. I have another electron over here. Its magnetic field vector points in this direction, north and south. And if I put a bunch of these electrons together, if I can get their magnetic fields to all orient in the same direction, then I have what we call a magnetic domain. I have a little sketch on the next page. In most materials, the magnetic domains are oriented randomly, given a net magnetic field of 0. So here, this represents a domain, a magnetic domain. And again, it's a group of electrons, a group of charges that are moving, and they all generate a magnetic field that's in that general direction. It might be that some of the electrons have a magnetic field that's in other directions, but the net sum of all the magnetic fields due to those electric charges moving is going to be in that direction. And if you have, a macroscopic material, bigger material, it's made up of all sorts of these magnetic domains, all connected together. In a permanent magnet, you make these magnetic domains line up so that you have a net magnetic field that is in the direction of the magnetic domains. So that's the difference between a permanent magnet and then just some random material. We all have magnetic domains, right? Even you and me, we have magnetic domains within us. We have magnetic fields. It just so happens that we're not a permanent magnet like this, but we're like the one above. It's non-magnetic because our domains all cancel out. These permanent magnets are created when molten metals solidify in the Earth's magnetic field. So you have a mountain or a volcano. That volcano spits out lava. The lava flows down, and then as that lava flows, its magnetic domains are within the Earth's magnetic field. When you have a molten metal, you can move the magnetic domains around at will, just with magnetic fields. And so that molten metal being in the Earth's magnetic field will orient all of its magnetic fields and all of its magnetic domains in the same direction. And then when the metal cools, it will they'll all be pointing in the same direction. So if I were to sketch out the magnetic domains, they would be pointing in this direction because the Earth's magnetic field also is in this direction. And so they line up with the Earth's magnetic field, and then when the molten lava cools and solidifies, it locks them into place, and then they can't move anymore. The magnetic domains, that is, can't move anymore. Electromagnets are similar, but they use moving charges in a wire to create a magnetic field. You have a current that's flowing through a wire, those are moving charges, just like the electrons in your atoms that are oscillating back and forth. And so those moving charges, if I have a current moving through a wire, will also generate a magnetic field. And this magnetic field causes the domains of the material to line up. We'll talk about this later. This is used in like a solenoid switch, and we'll see how that's useful later in this chapter. But imagine I have a piece of metal right here, a metal bar. It has magnetic domains that are just all randomly oriented, so that the net magnetic field of this equals 0. Here I'm going to introduce this variable. This is B, it's for magnetic field. It's a lot like an electric field. It describes the magnetic force, but we'll define it in just a little bit. So the magnetic field is 0 because those magnetic domains, they're all randomly oriented, and so they all cancel one another out basically. But if I put a current through this wire in this direction, then I get a magnetic field from the wire. It looks like this, and then that causes the magnetic domains inside the metal bar to line up. Y'all have done this, right? Where you take a nail and you wrap wire around it, and then you run current through that? You've done that? Yeah, in maybe 3rd grade, 2nd grade? You probably did, you just don't remember it right when you were in 2nd grade. Seriously? Alright, you take a nail and you wrap wire around it and you hook it up to a battery, and voila, what do you have? A what? You have a magnet, right? You have an electromagnet? Okay, I'm sorry. If you haven't done that, you should go do it. That's like every child should do that. Just wrap a piece of copper wire around a nail, hook it up to a 9-volt battery, and you have a little magnet you can pick up, paper clips or whatever. We're going to skip this little video. It was just like 3rd grade stuff. All right. Let's try these little quick tests. You'll have some basic information things about magnetic domains and what magnets do. Which of these best describes why some materials are permanent magnets? By the way, these materials are called ferromagnetic materials. What are some of these ways that they're called? What best describes why they're permanent magnets? All right, just a few more seconds. I'll stop. Stop at 40. Okay, let's see. That's right. B is the right answer. Materials found in the center of the Earth. Are you serious? Oh, it's okay. It's okay. Just because they're found in the center of the Earth, often the Earth generates a magnetic field because you have this rotating ball of charges, basically, and so those are magnetic fields as well. But it's not because they're located in the center of the Earth. Sorry. Every answer is okay, but B is right. Okay, which of these best explains why a permanent magnet is magnetized? All right, I'll stop at 35. 35. Okay, awesome. B is right. The magnetic domains of the atoms are aligned. If it was an electromagnet, it would be that it has a current going through it. The current actually causes the electromagnet to be magnetized. C is correct, that electrons produce their own magnetic field, but that's not why a permanent magnet is magnetized. everything has electrons that have their own magnetic field, but a permanent magnet is magnetized only because those domains are lined up. And ferromagnetic materials are always magnetic. That's not always true, actually. A ferromagnetic material, let's write this down actually. A ferromagnetic material is able to be magnetized, but not necessarily magnetic. If I know a good ferromagnetic material, I'll remind you, what does ferro mean? What is the root of that word? Iron. Okay, so iron is a good ferromagnetic material. It's able to be magnetized, but of course not all iron is magnetic. But if you wrap a piece of copper wire around and run a current through it, voila, you have an electromagnet. So let's move on to magnetic fields. We'll come back to this and visit it again with our concept questions. Okay, we use magnetic field lines to represent the strength and direction of the magnetic field. I'm going to use B for our magnetic field again. Remember, this is our magnetic field is a vector, so I'll put a little arrow over it. There are a couple of rules, and they're similar to what we had for electric field lines. The first is magnetic field lines begin at the South Pole, or excuse me, at the North Pole, and end at the South Pole. Goodness bless you. That's sort of like with the electric field lines began at the positive charge and ended at the negative charge. Although unlike electric field lines, remember if we had an overabundance of charge, like if we had twice the amount of positive charge as negative charge, then we had these field lines that would just sort of go off into space. That doesn't occur with magnetic fields. Why does that not occur? Why do you never, remember with this situation where we had like a plus 2q and a minus q, and we had field lines that went in this direction, but then we had extra field lines that went out like that. Why does that not occur with magnetic fields? Because of something we said already? I said it. I'm sure I guess. Because what doesn't exist? A monopole doesn't exist. A monopole doesn't exist. And if this was the case for magnetic fields, then that would mean that you would have an excess of North Pole to South Pole, or vice versa. And that doesn't exist. They always begin at the North Pole and always end at the South Pole. And then the second is that the density of the field lines is proportional to the magnitude. So, for example, I have a point here, A, I have a point here, B, and I have a point here, C. Where is the magnetic field greatest? At point A, B, or C? Where is the magnetic field greatest? Point A, B, or C? Y'all see the A, B, C? A right here, B, C. All right, I'll stop at 40. Okay, awesome, A is right. Where those field lines are closer, the magnetic field is larger. We have exactly the same with electric fields. Magnetic field does describe a force, just like electric field did, but we don't have a nice, neat little thing that describes the magnetic force, at least not right now. We'll get to that soon. Okay, a little bit about Earth's magnetic field. Oh, this is, gosh, did y'all do this? I don't remember. We're gonna skip the fifth thing. You can take a look at it later if you like. This doesn't go very well in class, unfortunately. All right, so the Earth's magnetic field, compass needle is a magnet with a north and a south pole. In fact, have you ever seen anybody out and if they don't have a compass, they just have a bucket of water and they put a magnet on a block of wood? You ever seen that? Yeah. Now you can do that. If you just have a bucket of water, put a piece of wood in it, and put a magnet on it, it will align with the Earth's magnetic field. So a compass is really just a magnet with a north and south pole, and the compass is different because it sits on this, this little pin that causes it to spin around. The north pole of that needle always points north, and the south pole of the needle always points south. All right, so if we were to imagine then the Earth as a giant bar magnet, then the south pole of the magnet would be at the geographic north pole, and the if we imagine that the Earth has a big bar magnet, so here's the Earth right here. Here's North America, South America, Europe, Africa, Antarctica. This is the south pole of the magnet. So I imagine this big magnet that sits inside of it. This is the south pole of the magnet, and then this is the north pole. So if I have a magnet over here, that is my compass, the north pole of my magnet will point towards the south pole, and the south pole will point towards the north pole. But I'm not talking about geographic north poles, I'm talking about magnetic poles. So the point is here that the geographic and the magnetic poles of the Earth are different. So at the geographic north pole is actually the magnetic what? South pole. But we call it the north pole because if we have a magnet, the north pole of our magnet points to the north pole. Y'all follow me on that? They're just switched. The geographic north pole is the south pole, but if I have a compass needle, the north pole of my compass needle will point towards the geographic north pole, which is the magnetic south pole. You follow me? Are switched. Right, so the north geographic pole actually is the south magnetic pole. Let me put that in words just to make it clear, because students sometimes get that confused. The north geographic pole is the south magnetic pole, and the south geographic pole is the north magnetic pole. And further, the north pole of a magnet, or the north pole of a compass, points towards the northern geographic pole. You can see a question just sort of exploring that. And we'll see some questions later in some of the Old Testament stuff. Just basic ideas that those poles are switched, and we call them north and south because our compass needles point in that direction. Okay, let's see. Want to watch this little clip? So the Earth's magnetic field does have a general direction from the North Pole to the South Pole, but locally it can be different. And you can go online where they've mapped out the magnetic pole and find the actual magnetic field at your particular location. Like you can put in your address and your zip code, and you can find out what is my magnetic field at this particular location. And you guys will do that in the lab where you actually measure the magnetic field here in Thibodaux, Louisiana. Yeah, seriously. You'll find what the magnetic field is here. But because of different things like geologic formations or whatever, your magnetic field can be different, say between Thibodaux and Lafayette. It can be slightly different because of the geologic features underneath the surface of the Earth. And other things like electrical wires and stuff too can affect your magnetic field. Alright, let's try this little quick test. Which pole of a magnet points towards the magnetic North Pole? Alright, I'll stop at 28. Alright, the south pole of a magnet points towards the magnetic North Pole. Alright, let's try just a slightly different one. Let's say, instead, which pole of a magnet points towards the geographic North Pole? Alright, I'll stop at 15. 18. Okay, awesome. B is the right answer there. Because the geographic North Pole is actually the magnetic South Pole. And so a North Pole of your magnet is going to point towards the geographic North Pole, which is why we call it the North Pole, because North Poles of compasses point there. Alright, let's see. You know why they told the pig to leave the party? He was bored. Okay, let's talk about the magnetosphere. Just need to know basic stuff about the magnetosphere. The Earth magnetic field protects us from a variety of things. Protects us. Are there these charged particles that come from the sun that travel at very high speeds? These charged particles. And they come zooming towards the Earth as part of the solar wind. And when they impinge upon the Earth's magnetic field, these charged particles, a lot of them will just sort of go out into space because they'll be deflected by the Earth's magnetic field. Sometimes you'll get these charged particles will come into the Earth's magnetic field and then come down into the atmosphere like this at different parts of the Earth. What does that cause if I have these charged particles that come into the Earth's atmosphere? I mean, you've probably never seen it, but do y'all know what it's called? The aurora borealis. When these high energy charged particles go in the Earth's atmosphere, they emit light, or they emit radiation called Cherenkov radiation. And that's what creates the aurora borealis. These high energy particles from the sun that strike the Earth's surface or go into the atmosphere. See, I have a little video about a substorm where it'll sort of tear away these magnetic fields. Let's go ahead and we'll just watch it. It's very interesting. Everything sounds smarter when you say it in a British accent, right? This is an aside, but we took this trip to Mississippi, and my kids, they're good kids, right? But they in the car and they start fighting or whatever. Mainly my daughter complains about my older son. And so I told her that she could only complain if she complained in a British accent. But of course, she can't do a British accent, but then she couldn't complain at all because she'd just start laughing. Maybe we should do a similar thing. Whenever we're going to complain about something, we should say it in some goofy accent. That's what I'm thinking about, y'all. Okay? So, let's see, where are we? Okay, so magnetic forces. A charge moving through a magnetic field experiences a force. the magnitude of this force is given by this, that F is equal to QVB sine theta, where V is the speed of the particle, B is the magnetic field, and Q is the charge of the particle. So our force is given by this, QVB sine theta. The angle theta is the angle between the magnetic field and the velocity vector. Nothing funky with that. If you have an angle between your V and your B, then it'll be given as it is. Sometimes we'll find that if our angle is equal to 90 degrees, what is the sine of 90? What is it? It's equal to 1, right. So if theta is equal to 90, then our force is at its maximum value. If theta is 0, the sine of 0 is not 1, but it's 0. So if our velocity vector and our magnetic field vector are in the same direction, there is no force at all. There is no magnetic force. So remember that. Sine of 90 equals 1. Sine of 0 equals 0. So the result of that is that if F and B are parallel, or excuse me, if V and B are parallel, there's no force. The SI unit for the magnetic field is the Tesla. Of course, this is after Nikola Tesla. You've probably seen the movie. What was it called about him? You haven't seen that movie? It's like something. The Prestige. The Prestige? Seriously? Like you've seen that other movie, but you haven't seen The Prestige? Oh, for goodness sake. Anyway, we'll hear about Nikola Tesla later. He was pretty important in developing our country's use of AC electricity, and we'll hear about that later when we get to that topic. Sometimes the magnetic field is expressed in other units in Gauss. I won't use Gauss, but sometimes you might see it. 1 Tesla is equal to 10 to the 4th, or what's that, 10,000 Gauss. We're going to use the right-hand rule to determine the direction of the force. We sort of used the right-hand rule a little bit last semester, but we're going to use a lot in this chapter, so you're going to get pretty sick of it. But it is useful. I think it's useful in the sense that it really helps you to think spatially a lot better about in 3 dimensions. And so that's one reason. And then the other reason is just, well, you know, that's how we determine the direction of magnetic fields and the forces that they play. So the right-hand rule works like this, and there are a bunch of different iterations of this, but you let your fingers of your right hand I'm going to abbreviate RH. The fingers of your right hand point in the direction of the velocity vector. All right, so some key things. Right hand, not your left hand. The fingers in the direction of the velocity. So your fingers of your right hand point in the direction of the velocity vector. You fold your fingers towards the magnetic field vector. And then your thumb gives the direction of the force. Now some examples for you. But like your fingers of the right hand point in the direction of the velocity vector. You fold your fingers towards the magnetic field vector, and then the thumb gives the force. Make sure you're using your right hand whenever you're doing the right hand rule. Like Miss Perry said, you should always carry your right hand in your back pocket. That's why, because you'll use it along with your positive test charge for a variety of things. Okay? So for example, oh, first of all, this assumes the charge is positive. If the charge is negative, you just take the opposite direction. And then let's just get these direction vectors. I'll hand your tests out. To denote the negative z direction into the page, use a symbol that looks like an arrow going away from you. So this is supposed to look like the fletching of an arrow, right? Those feathers, like it's going away from you. And then this is the positive z direction, and this is supposed to look like an arrow coming straight at you. You ever had an arrow coming straight at your face? That's what it would look like, just a little point. Okay? Sometimes you'll see a magnetic field represented like that, or sometimes you'll just see it with dots, and I'll leave the circles off, especially if I'm denoting like a general area. Let's do these, a couple of these, okay? We have just a few minutes, so, and then I'll hand out your test. So for example here, let my fingers go in the direction of V of my right hand. They don't go this direction, they have to go this direction because it's in the direction of V. And then they fold towards V. Now notice I can have my hand like this, but I can't fold it towards V in that way. So I have to have it like this. And so my thumb gives the direction of the force, which is out of the page. And out of the page is going to look like this. That's my force. What would be the direction of the force for this scenario? Fingers in the direction of V. V here is away from you. It's in this direction. So what would be the direction of the force? Now you know that it can't be either in the y or the z direction, so it either has to be left or right, because these vectors are all orthogonal. If your y direction is taken up and your z direction is taken up, then it has to be the x direction. Left or right, y'all think? Let's see. So V is in that direction. I have to flip my hand around like this because my magnetic field is fold, so it's going to be to the right. So my force here is to the right, and then for this last one, V is out of the page, like this. V, I fold my fingers towards V like this, and so my thumb gives the direction of the force. What is that? To the right? It's to the right, right? Am I right? Yes, to the right. So that's my force. All right, we'll come back to this. We're going to do a bunch of these, so you'll have lots of practice. There's some in the homework, too. Right now, I'm going to hand back your test.